Hello there everyone, this is a video about the repair of a Hewlett-Packard 8920B radio test set. The fault that was reported with this particular unit was no power up at all. When you press the power switch, there's nothing, no power whatsoever, no fan running, nothing. So anyway, looking further into it, I found that the power supply unit, which this is the unit that I've taken out, normally sits at the back in this void area. This particular power supply had failed, and it was immediately apparent upon looking at it what had actually failed. There's a cluster of components here, resistors, transistors. They'd all burned to a crisp, really bad. It looks nothing like it does now when I took the unit out. This was just a black char. Likewise, the IRF540 switching transistor that's mounted on this heatsink that switches the primary of the transformer would also completely blasted, parts of it missing. The two smoothing capacitors are domed. This one in particular was really bad, but that one wasn't so bad. All the capacitors on the output look fine, so I didn't think there was an issue there. The rest of the circuit board was okay. The trouble was, because these components had all burned to a char, I had no idea what values the resistors were, what the part numbers of the transistors were, because there were holes in the transistors. So I really struggled to, try and do a repair myself. Anyway, to cut long boring story short, I found a company in the UK that said that they repair these. I sent it off for repair. I didn't hear anything for a very long time, many months, and then suddenly I gave them a call to find out what had gone off, and I was told, but because they don't have a diagram, they couldn't do anything further with it. So unless they had a diagram, they wouldn't be able to do any further repair. So I had looked round for another company at the time to see whether anybody else had repaired these, and in doing so I managed to find, for some reason at that point, I don't know why I couldn't find it to start with, but there was a forum, I can't remember if it's EV blog or Vigilant forum, that actually had a link to a diagram for this power supply, which is this here, and I'll post a link in the description below. Now I've got the diagram, so I sent this to the chap who was trying to repair it for me, and then he thanked me very much for doing that, and obviously help him out with any further repairs that he might do on other customers' supplies as well. So just wanted to help him. But what had happened is that he started to replace all the components, which he did a very good job of. He replaced all the resistors and transistors that are blown. For some reason he didn't replace the capacitors on the input or the output section, because this one was only domed slightly and the other looked okay, and he must have measured them and thought, well, the measure fine. I get the main part of the repair done first perhaps, and then replace the other bits after. But anyway, he did replace these components here, and he couldn't get it going, because I rang him up again to say how's things progressing, and he says, oh, I'm sorry, I can't fix it, I'm really sorry, I can't spend any more time on it because it's such a nightmare job to do, so I'd like to send it back. And I said, well, fair enough, I'll pay for the repair, your labour and all what you've spent on it so far. To be fair, you've done a good job at, up to that point. So I got the supply back. I think I paid £32 including VAT and postage and packing for it to be returned, and including the repair. So I thought, that's not bad. Anyway, because I was now armed with a diagram and I can spend a lot more time on it, I started to look at the diagram. Now, this section here, which you can see in the centre of the screen, all these components that you can see there are actually the components which were frazzled. So this is a main switching transistor. These transistors here are located near that toroidal transformer, which is this, and all these resistors were all frazzled. So I just thought, well, I'll see what voltage we've got here on this potential divider, because if we look at the circuit more precisely, again, we've got mains input coming in, bridge rectifier, smoothing capacitors via filters, and then we've got a resistor here, and then another resistor of a very low value in comparison to that one, and then across this resistor. So the potential dividers here via this 39 ohm resistor into the IRF, and I wasn't getting a supply here. So I started to look at things like, for example, this transistor taking the line down via the transformer, which I doubt because this is a new one. This Zener diode, looked at that independently and that worked out to be fine. So I was really struggling at one point. I couldn't get any voltage here at all, and what I ended up doing, just as a way of being able to just again unravel it piece by piece, is this resistor here. I lifted that and then reapplied the voltages again, see whether I could get a potential divider voltage in the middle. There was no supply whatsoever. The 15 volt clamp here, I would at least, according to R1 over R2, if we had those two resistors together as one resistor, and this is R2, we should be getting, if there's 350 volts roughly on the reservoir caps here, we should be getting about 12 to roughly 14 volts DC there. And there was nothing, absolutely nothing. Anyway, it turned out that the chap who'd repaired it, probably in a rush to repair it, had made a little bit of a mistake, which I shall show you on the circuit board in a moment. And that is, this value of resistor would have been only 39 ohms, and this value of resistor here, which is obviously in the K value range, it got these two swapped the wrong way around. So in other words, there was a 39 ohm resistor here instead of there. So basically what it meant is that there's no way in a month of Sundays with the high values of resistors here that this could develop a potential across a 39 ohm resistor. So that's the reason why there was no voltage there. Now if we have a look at the values and the location on the circuit board, one of them is called R10, which is a 39 ohm resistor, and the other is called R12. Well, if we have a look on the circuit board here, you might be able to see it a bit better if I just go over it. There is a line, it says R10, and then there's a line pointing to the resistor, and then this one is R12, which is written on the board down there. Now because there's a resistor and a point to it, and then there's a line with another R number written, I think it's very easy when you're rushing it to make a mistake in assuming the one to the right is actually the one for the left and vice versa. So what he'd done, he'd obviously put them in the wrong location. I then changed them to the correct location, and lo and behold, the thing started to work. But what I've done despite that is I've replaced all the electrolytics. So the two main reservoir capacitors on the input, all the output capacitors I've replaced, even though they look fine and they weren't vented, they hadn't leaked or anything. I've just changed those. Now, one of the interesting things about this supply is the lack of information that's even contained on the diagram, because how this supply works is that you can provide either mains 240 volts, 110 to 240 volts AC here on the IEC socket, or on the white DC socket at the rear you can supply, I think it's between sort of 13 to 36 volts DC from a battery. Now if we just take the casing point for the battery supply here, that enters the supply and is switched by two big transistors here and here, which is hidden behind this board. And this transformer, which is located where this was pointing to, is switched on the primary side, and this is a step-up transformer, which then goes through a bridge rectifier and then supplies voltage to these two reservoir caps, and will charge them up to around about 350-360 volts DC. So in other words, by powering it by DC, it effectively puts what would be a mains potential on these two reservoir caps, and then run the supply as if we had a mains input anyway. So that's how that works. So this is a DC control PCB on the rear, that's a step up transformer, and then we go through to supply a stepped up switched DC supply to these two reservoir caps, which in turn provide the main switching current and voltage for the switching transistor. Now on the diagram, when I was looking at the diagram, the way the circuit works operates on feedback obviously, and if we just have a look at the output section just for a moment, we can see that there's a transformer here, output, and a sample of this is fed back obviously to the input side, which is this transformer. So that's the primary and secondary windings of the same transformer. And if we look here just on the output directly of the transformer, on the secondary side of the switching transformer, we've got a signal that's fed in to what appears to be some kind of signal amplifier, which is powered from the 5-volt rail of the output, and then it's switching this transformer, which then goes back to here. Now what we've got is with a little bit of misinformation in the fact that the DC control board, which is shown there, this DC control, there isn't a diagram for that particular circuit board, which is the board at the rear here, which is stood on its end. So the only diagram that I managed to get is the one for the main board, but you can clearly see the general operation of it. This is a DC input jack, which then via a series of switches to isolate the mains side as well, because obviously we don't want any voltages going back out. But anyway, the switches are configured in such a way that when it's operating on DC, it isolates the AC side. It then passes that through various filtering into two switching transistors, which the inputs to these are controlled from the DC board here, the plugs that are for that. It switches obviously this step-up transformer, which I've just shown you on the PCB, via rectifier diodes, and then the line goes up to supply the main reservoir caps with the high voltage DC. We've also got another transformer which then creates a regulated supply for the DC control board independently as well. Now I was struggling to find out how the DC control board, which is there, actually controls the oscillation and the feedback, because if you notice, there is no connection, when you study the diagram very carefully, between the DC control board and the main switching sections of the supply. There is just literally the 5-volt rail output of a supply, which is fed back to the DC control board, but the DC control board appears not to have any influence at all on the oscillation or the feedback, if you like, control for the main switching side of it. Now all I could gather in looking at the diagram, which is highlighted in pink, is there are two voltage references, and I think while ever those references are there either side, then it will be in lock, if you like. It will be perfectly stable with the input and the output. However, the issue that we have is with the lack of information. There doesn't appear to be, from what I can see, any way that the DC control board physically controls the oscillation of the main switching side when it's powered from mains. It appears to be self-governed using the two voltage references that are highlighted in pink. So I was really struggling to understand, surely the DC control board that's mounted on the rear of the PCB isn't just there for the DC input side, it's there to control the switching circuit and everything else. And the feedback transformers here, and there are 3 taps on it, which is obviously the green wire, the red, and then this darker red or brown colour. So I was assuming that one of the taps on there went back to the DC control board, and that influenced the switching frequency to compensate for the output current draw, etc. But it doesn't appear that that's the case, according to the diagram anyway. There's no control from this DC control board here to this part of the circuit. It's just that whenever there's a current draw on the output, the DC control board monitors a 5-volt rail, and if it sees that the 5-volt output leaving the supply here has dropped, then it will increase the current drive, if you like, to this transformer to then compensate for the DC fall, if you like, on these 2 reservoir caps, and thus boost them up higher, because it doesn't take much current draw from this to reduce the voltage that's on these capacitors, because it's quite a low current drive. Anyway, that's my theory of it. The diagram, as you'll see when you study it yourself, does not show any control specifically for the feedback derived from the DC control board, which is stood at the end on its own socket. So my recommendation with these supplies is replace the reservoir caps on the input and the output. The PCB, if it's burned here or you've got blown components, change them all anyway and you should be okay. I would run it up on DC whenever you're doing fault finds or tests on it, simply because the DC drive to these 2 capacitors is quite low in current, and you can set your power supply to current limit so that if, for example, there is a short circuit or a major problem, you're unlikely to blow it up, because you only need a very slight load on these 2 reservoir caps for it to sort of not struggle, but you can definitely tell that it's trying to maintain the charge in them. And indeed, one of the safety things that I must warn you about with this supply is that there is no bleed resistors on these 2 caps, and down here is a bridge rectifier on those 2 heat sinks, and essentially each heat sink is positive negative. With the way the diodes are orientated on that heat sink, those 2 heat sinks are positive and negative terminals in relation to these capacitors. So if you were to touch those while these are charged, you're going to get a very nasty shock. And by me introducing a 2K resistor just across these capacitors to discharge them, actually puts this DC switch inside here under some load. So the current that it provides in this portion of the circuit is actually quite low. So it's my recommendation that while you're doing any repairs and testing, is use the DC input first to try and diagnose or sort problems out on the main switching side before you introduce mains, because mains input is very unforgiving. Obviously in this country, in the UK where I am, we have 13 amps at 240 volts AC, and it doesn't give you much room for error. If there's any problems, you're just going to get fizz bang and bush, that's it. It's going to be a cloud of smoke and components destroyed, all sorts of problems. Whereas when you power it from the DC side, you know, if you were to introduce a short or there was a fault somewhere, the DC switching side will be really under strain, and you can tell that, so it has more give in it, and it doesn't need much current in a fault condition for it to totally flatten the charge in these capacitors. So it's easy to diagnose faults without causing catastrophic failure. So as I say, I would power it from DC first to make sure the supply is all running and correct, then move to the AC side if you're confident that your repairs worked. So after that, the power supply was fitted back in the unit, having more or less come to the opinion that we'd repaired it. So I put it back in, put mains to it, switched it on, and then all you could hear was this horrendous screaming sound. It was just making a horrendous scream while it went into fallback, shut down mode, and then screamed again, switched off, screamed again, switched off, screamed again, and so I needed to look further. Now this power supply actually has another regulator which is mounted inside the main unit, which this supply feeds, and then the regulators used then to produce a more stabilised 5 volts, plus 14 volts, minus 14 volts, plus 43 volts, plus 5 volts, and those supplies are then sent out from the regulator board to the different parts of the unit for all the supplies. Now this is a regulator board here, and we have a minus voltage regulator, and then we have some positive voltage regulators for the 5 volt, plus 14 volt, minus 14 volt rails, which are the high current rails. And what I found is that just by merely connecting these, the output of the main switching supply to this, it loaded it, and that seems to be what causing the fallback issue on the power supply. But the way that the orientation of this board is made up with regards to the input and output connector, it's one connector. So to isolate any of the inputs or any of the outputs, you have to back the pins out, the plug, one by one, to try and find out whether it's the regulator board itself that's defective, or whether it's what's driven from the regulator board, as in what's in the main unit. So each supply rail on the output was backed off, and that didn't resolve the issue with the fallback switching off of the power supply. So the input was done the same, and I managed to find, I think it was a 14 volt rail, plus 14 volt. When you remove that, then the supply came up, the fan started running internally, the rest of the supplies were more or less there, and I just thought, well, that's it then, it's a plus 14 volt rail. Now one of the things with this test set is the information isn't that good. It's an assembly level repair manual, and it's not particularly very well explained with regards to its technical operation, so you've got to do a lot of figuring out. So this is the main supply that we've just been talking about. This is a regulator board which I've just shown you, and what led me down the garden path, which has obviously led me to make some mistakes, is that I was assuming that the 14 volt rail, or the plus 13.4 volt rail, was the actual issue, which is this rail here. Now I found when I disconnected this wire, the rest of the supplies all came up insofar as the output of the power supply, but the output voltages here weren't there. So although I'd lifted this rail, in effect not getting my 14 volt output or 12 volt output there, I got my supplies, I thought I would have my supplies on the output here, and they'd disappeared as well. And what it is, this is actually an enable line, because feeding off this is a 10 volt reference, and the 10 volt reference is supplied to each of the 3 regulators. So without the 10 volt reference, then we wouldn't obviously get an output from these 3. So that's just one to be aware of. That you may think that that rail is just an independent rail all on its own to supply a unit supply to a PCB or a number of PCBs mounted on the motherboard. It is, but it's also the supply for the 10 volt reference, which is on the regulator PCB, and without that reference none of the other regulators would work. So having resolved that issue and dealt with that and understood that, I then went to the outputs here and disconnected these 2 from the circuit board. So we were just looking at what the output of the regulator was doing without a load on the motherboard, and I found that with the DVM just on the output, the minus voltage regulator had a plus 1 volt supply coming out of it, not -1, not -14 or 12 like it should be, and the other regulators didn't have an output either. Anyway, upon further examination of this regulator board, I found that again we've got a precision reference here, 10 volts, that was working okay. This is the driver IC for these regulators, and that appeared to be functioning, but yet these regulators had supplies to them, and a 10 volt reference was supplying the right voltages, biasing conditions to these regulators, but it didn't seem right. There was no output, but there was an output if there wasn't a load. So if you just had the high resistance of the DVM measuring the outputs of the regulators, there was a supply voltage there, not what it should be, but near enough. But when you put something like a 2k resistor across the terminals to the multimeter, then there was no output voltage whatsoever on the regulator outputs, apart from on the minus voltage regulator, which had a +1 volt, which seemed to me to indicate that there was a gate drain leakage from the bias applied to the regulators that was making it out onto the output. So what I've done, where I'm at now, is I've ordered these 3 devices. I've ordered another IC here, and I have checked this IC and it's producing 10 volts precision reference. So I think that perhaps when the power supply went bang, something's happened with these regulators. I'm not sure what, and it's without the detail about this circuit board in particular. I've worked everything else out. One of the advantages is that it's got the voltages written on the back, so you can actually measure what are the inputs and outputs on the board. So when I get the regulators and replace them, as I said, we've got minus voltage and 2 plus voltage regulators. We'll see whether it works, but it does seem a little bit strange, I must admit. Very, very strange indeed, that those should go as well, unless something's happened with the supply output, suddenly gone incredibly high, a spike or something like that, which I don't know if that's happened. But anyway, as part of my fault diagnosis as well, I took out all the modules that's inside, and all the modules, the spectrum analyzer, the RF analyzer and everything, they all line up in there. I removed all those to check to see whether one of those was causing the issue. These are the power cables from the regulator board which plug onto the motherboard. So they were the ones that I removed, which are the 2 sockets I showed you in the diagram. There are some audio analyzers and things that are under here. I've had these out, I've had the controllers out and the memory boards, just to see whether I can find anything obvious where there's tantalum caps or anything like that. I've measured across what will be the supply rails to the motherboards to check for shorts, because sometimes tantalum capacitors on the motherboards and plug-in boards can go short circuit, or some other fault can develop which causes a short on the supply rail, and there are no shorts on the motherboard supply rails. But what I did find that was quite worrying is on the side here we've got some screws, which just in this section here is a controller, the main controller for the test set, and it does have a warning label which says only fit yellow screws here. Now the screws that were originally in there were not yellow screws, and I only noticed when I took this plate off to inspect the motherboard that resides under here that the screw was touching the motherboard. It wasn't pressing on it and causing any damage to the motherboard, but it was just touching it, not firmly but gently touching the board. Luckily though, in the areas where these screws that were not yellow coloured were in place, it hadn't caused any damage to the circuit board, and not only that, there wasn't any print on the circuit board in the area where these screws touch. So I'm not sure whether an individual prior to me has been trying to repair this at some stage in the past and put the screws in the wrong location. But if that being the case, I should have found the yellow screws elsewhere on the test set, because obviously the screws that were meant to be, you know, in other parts of the unit would have ended up here, and likewise these yellow coloured screws would have ended up, say, down here or wherever the modules are where they've had them out. And I can't find any yellow screws, so I do wonder if the screws that were in there originally are actually correct, and Agilent knew that they wouldn't cause a problem, which they don't obviously. But anyway, I've left them out just for now. So I'll come back to you in part 2 with what I find, and we'll see whether or not those regulators that I've ordered actually turn up and work when they're fitted, and hopefully we'll get the test set running again. So thank you very much for watching the video. I realise there's a lot to digest with that, and I'll put a link in the description for the circuit diagrams and the spec for the power supply to help anybody else who's in a similar position. So stay tuned for part 2.